this video, I'll show you step by step how to build your own agentic coding assistant from scratch. An agentic coding assistant is an autonomous AI system designed to handle the full lifecycle of a coding task. It analyzes your entire project to understand context, creates structured plan to solve a problem, and uses a suite of tools to read, write, and text code directly in your environment. It doesn't just suggest a solution. It implements it, verifies the results, and self-corrects until the goal is achieved. All agentic systems have at least 3 parts: a brain, tools, and memory. The brain is the core intelligence. It's a large language model like Claude 3.5 Sonnet or Gemini 1.5 Pro. It takes your messy human instructions and turns them into a logic-based plan. In an agent, the brain doesn't just give one answer. It uses a loop called react. It thinks, takes an action, looks at the result, and then thinks again. It decides which tool is right for the job. If the brain is the thinker, the tools are the hands. An LLM by itself is just a text generator. It can't actually touch your computer. Tools are the bridge. There are different types of tools, like file system tools. These let the AI read, write, edit, or remove your coding files. Then there are terminal tools. These let the AI run commands like npm run dev to see if the code actually works. Finally, search tools help the AI find a specific function hidden in 100 different files. So the AI can now think and access your data, but without a memory, the AI would forget what it did 2 seconds ago. That is why memory is also important. It keeps the agent from getting dizzy. It allows the agent to look back at what it already tried, learn from the results, and stay on track until the job is finished. Building an agentic coding assistant in 2026 is incredibly valuable because in the AI revolution, the world is being split into 2 distinct groups. On one side, you have the consumers, the people using AI in their daily workflows to keep up with their jobs. On the other side, you have the builders, the AI engineers, and companies who are actually architecting the market. While everyone is worried about AI taking jobs, the builders are the ones creating the tools like Cloud Code, GitHub Copilot, Cursor, all generative AI tools for social medias that the rest of the world is paying to use. The future doesn't just belong to those who use AI. It belongs to those who build it. Stop asking if AI will replace you and stop asking how you can join the group that is actually building the future. Today, we are moving you from the side that fears AI to the side that commends it. And over the next few hours, you aren't just following a tutorial. You are architecting a production-grade agentic coding assistant CLI from the ground up. We are going to implement the 3 pillars of a true agentic system. First, the brain of the system, where we define how it reasons, plans, and corrects its solve mistakes. Second, giving your agent hands to interact with the real world, from file systems to terminal execution, all in a safe, sandboxed environment. Finally, a stateful layer that ensures your assistant never loses context or forgets a single line of your code base. By the end of this session, you will stop being a consumer of AI and start being the engineer who knows how to build and design AI applications. Alright, let's start building. As we said, we'll start by implementing the brain of our agent. But before that, what are the prerequisites? We'll be using TypeScript as the main programming language. You just need to know basic JavaScript like variables, loops, functions, core functions of JavaScript for the file system especially. And more importantly, OOP, Object-Oriented Programming. Then the first thing to do is to create an empty folder where you want to start your project. If you have been following this channel, you already know what NPM is. It is a Node.js package manager, which allows us to use thousands of libraries available for free. So here we are going to use the command npm init to initialize the project. This will ask you to set the package name, the version, description, the package entry point, the test command, empty for now, git repository, empty for now, keywords, CLI, offer, license, type of package. By default, it is CommonJX. Then hit enter. After that, we can go to package.json to see the summary. You can still change all the values we just set. Then go to the terminal again and we'll install some packages like TypeScript. We'll be using TypeScript for type checking and emit. Type checking allows the TypeScript compiler TSC to scan your code to ensure you aren't passing a string where a number should be. Emit allows the TypeScript compiler TSC to transform your TypeScript files into executable JavaScript files that the browser can read. Next to TypeScript, we will also need TS Node. JavaScript is primarily a client-side programming language. It originally worked only in the browser, but with Node.js, it is possible to run it on the server as well. So, to run your TypeScript files on the server directly without compiling them into plain JavaScript, we use TypeScript nodes or simply TS Node. TS Node is an executor. It allows you to run TypeScript files directly in your terminal without manually compiling them into JavaScript first. We also need to install types for every function Node.js provides using @types nodes. Then add -d. -d is a shortcut flag for --save dev. When you include this in your install command, you are telling npm to categorize that package as a development dependency. In case you don't know, when you build an app, you have two types of packages, dependencies and dev dependencies. Dependencies are required for the app to actually run in production. On the other hand, dev dependencies are only used while you are building and testing the code. Great, now let's move on. npm will install these packages and we can open the package.json to see what version we are using for each dependency. After that, we run npx. This is the node package executor. Its job is to run a package. First, it looks in your node modules. If the package is not found, it looks at the npm registry online. In our case, the SC is already installed with the npm install TypeScript command. Then we can use this TypeScript compiler tsc to initialize our new project by creating a tsconfig.json file in your current folder. Now, let's open this file. This is a TypeScript configuration file. It has many options like compiler options. This is useful because JavaScript, like many other languages such as PHP, has different versions, and a new one comes out every year. For example, PHP 3, 4, 5, 8. But unlike PHP, we don't say JavaScript 4 or 5. Instead, the version is handled by the term ES, which means ECMAScript. We can say ECMAScript 1, 2, 3, or we can say ECMAScript plus a year, like ECMAScript 2026, for example. So here, in compiler options, we first have the option root directory. This tells TypeScript where your source code lives. It ensures the folder structure inside source is mirrored in the output. So basically, our code source is inside the source folder. Then the out tells TypeScript where the compiler tsc will put the generated JavaScript files and any associated output. This will be in the dist folder. Then we also need to set the lib and types options. The lib setting provides the definitions for global objects. Global objects are variables, functions, or objects that are built directly into the JavaScript environment. They are always there. They are always there, meaning you can use them in any file in your project without having to import or require them. These exist in both the browser and Node.js because they are part of the basic JavaScript language. For example, console is a global function. You don't need to import anything to use it. Another example is process. This is a Node.js global object we use to read environment variables using process.env. So here, by choosing ES next, we are telling TypeScript to use the absolute latest cutting edge JavaScript features that were approved. Also, types node tells the compiler to only recognize Node.js globals, not browser ones. Why? Because by default, JavaScript is client-side and already defines browser globals automatically. Let's move on now. We are also going to add more options like include, which tells TypeScript which files it should consider. The exclude, on the other hand, specifies which ones it should ignore. After that, we are going to set up scripts in package.json. By default, npm installs the test script. We can add more scripts like build. The build script uses TSC, the TypeScript compiler. It will check for TypeScript errors and also generate compiled JavaScript files and sources. The start script should be called after the build command. It just runs the compiled JavaScript files and sources generated by the build command using tsnode. The dev script runs your TypeScript files directly without compilation using tsnode only for development purposes. After that, we can now create our first folder inside the source folder called CLI. CLI is the main folder of the app, and inside it, indexed.ts is the starting point of the app. This is the main file that runs when your CLI command is executed. Open it, and inside we are going to print content to the terminal or the browser console. To print or display content in the terminal, we use the global object console and then call the function console.log. This function takes a string or text. So add the text hello AI coding agent, for example. Then run in your terminal npx tsnode and the index.ts path. This will run the index.ts file automatically without compilation. As you can see, the terminal shows the text we set inside the index.ts file. This is great. Now, the next step, we are going to create the brain folder called agent, and inside it, a file called agent.ts. Here, we export an async function, runAgent, the main agent execution function that takes the user's instruction and returns the final result as a string. Inside this function, we first read configuration values like API key. To read this value, we use the node.js global objects process, then access env. This allows us to read variables we are going to create in the environment file. But before that, we need to load these variables using .env configuration. So install the package with this command npm install.env. Then import the .env package directly in your file. After that, we can set up the configuration using .env.config function. It takes an object. This object has a key, path, that specifies where to find the environment file. It uses path.join. This is a safe way to glue folder names together. It takes two arguments. First, process.cwd function. This is important because it always looks in the root folder of the project, no matter which folder you are currently inside. Then the environment file name. by convention .env, but you can rename it if you want. By default, when we initialize the project, we use common JX, which uses the syntax require and module.exports. But now we want to use the latest syntax like import and export, which is the modern standard. So for that, we need to set in the package.json file or key type with the value module. That's it. Then we can continue the run agent function by setting the rest of the environment variables like module name, base URL, and app URL. Next, create the env file at the root of the project and set those variables we just created. We'll be using the Open Router API key. Open Router is a unified gateway for artificial intelligence. Instead of signing up for OpenAI, Anthropic, Google, and Meta separately, you sign up for Open Router once and get access to almost every major AI model through a single API. So go to their website and click on Get API Key. Maybe you should log in first. Then create a new API key, copy it, and paste it into your .env file. For the model name, Open Router provides free and paid models. We'll start by using a free model. These free models have rate limiting, so this is just for learning purposes. For production, you definitely need to use paid models like Gemini Pro or Claude Sonnet. So go to models page and search for free. Click on the icon to copy the model name, then paste it into your .env file. Then, for the Open Router base URL, add openrouter.ai/API/v1. And for the app URL, just add your GitHub repository or your app URL in localhost. Once we set all these variables, we can perform a validation check to make sure the required variables are set before continuing. Then we can send a request to the Open Router API by using the chat OpenAI class from LangChain. What is LangChain? LangChain is an open source framework designed to help developers build applications powered by large language models, LLMs. LangChain is organized into specific modules that handle different parts of an AI app. Models provide a unified interface to talk to any LLMs like GPT, Claude Sonnet, Gemini, and so on. Prompts provides templates that help you structure your instructions so the AI gives better results. Chains provides the ability to link multiple steps like summarize or PDF and translate the summary, then send an email. First, let's install LangChain for OpenAI. This class sets an object. This object has model name and temperature. In the world of large language models, temperature is a hyperparameter that controls the randomness or creativity of the AI's output. Low temperature makes the model generate safer content. On the other hand, high temperature makes the model more adventurous and creative. Max tokens 4096 means around 3000 to 3500 words maximum. This limits the length of the AI's response. Then there is a configuration object. This is the most critical part of the code, the Open Router bridge. Here we configure the request settings for Open Router. We point the code to the Open Router base URL. Then we also set our default headers config object. It includes authorization key. Open Router expects some standard bearer token format. By putting it here, you ensure that every single request sent by this LLM instance carries the correct identification. HTTP referrer. This allows Open Router to track which apps are using their service. X title represents the project name. Then I set the try-catch statement. First, I call the invoke function that triggers the execution phase of the brain we configured earlier. This is the moment our code actually leaves our computer, travels across the internet, and returns with an answer. What actually happens? LangChain takes our messages array, which contains both system and human messages. For a system, this content is the prompt. You are a senior software engineer assistant, prioritize safety and minimal code changes. Then for a human, the content is the user's input. These messages are converted into a specific JSON format that Open Router understands. LangChain attaches your API key, temperature, and max tokens, wraps them in a HTTP post request. The request goes to the base URL endpoint, and Open Router looks at the model name. Open Router forwards request to the actual model provider. The LLM provider receives the prompt. The GPU runs with our temperature setting to predict the next tokens one by one until it hits the max tokens limit. In our code, we await until the full answer is generated. When it finishes, it returns a base message object. This object contains content, the actual string of text the AI wrote, response underscore metadata, information about how many tokens you used, and which specific provider open router used to fulfill the request. Usage underscore metadata, a clean breakdown of the billable tokens. So for now, we just need to return the content. You can use the other values like response underscore metadata and usage underscore metadata for cost tracking. We'll do that later. Even though you expect the AI to return text, the response.content in LangChain can sometimes be an array of objects. By wrapping it in string function, we are forcing whatever the AI gives you into a standard text format. This prevents your app from crashing if the model returns something unexpected. Then, if something goes wrong, just throw an error and display it in the terminal. Once we create that basic brain logic, we can test it right away in indexed.ts. So here, just delete everything and create an async function main that calls the run agent function and passes to it for now a string. Then display the result in the terminal. If something goes wrong, also display the error. Now we can replace the default string input with a real value sent by the user. So call the argv function. Process.argv is an array that contains everything you typed into the terminal when you started your node.js program. It allows your code to read command line arguments. So here we just split the user's command node test /cli/ indexed.js prompt into items. First item node has index 0. Second item index.js path has index 1. Third item the prompt has index 2. The third item represents the user's prompt that we should pass to the run agent function. So we just pass the input to run agent and display the result. We can test this quickly. Open your terminal and run npx tsc index.ts plus entry point path plus the prompt. Hit enter. First, it loads the .m file, then performs the API call that returns a response to our prompt hello. Great. Now, since we were using TS Node to run TypeScript files with compilation on the server, we are going to switch to another node executor, which is txs. So go to package.json and replace TS node with txs. Why? Because txs is a newer version that does the job faster. Besides, TXX is built for the modern era. It handles import and require automatically without extra configuration, unlike TS Node, which requires some extra TypeScript configuration. So in short, TXS is faster, requires zero configuration, and natively supports EXM and built-in JavaScript features. Great. Now it is time to focus on the tools of this agent. So create another folder called Tools inside the source folder. Inside this folder, create a file called agenttools.ts. Inside this file, create and export a function getAgentTools that will gather all the tools we are going to build. So it returns an array of objects that follow the structured tool interface. This interface comes from the LangChain package. So let's install it quickly by running npm install at langchain/core. Then we can import it. And then our getAgentTools function by default returns an empty array because we don't have any tools yet. So now let's create our first tool. This is going to be responsible for reading files. So here, export a class called readFileTool that extends the structured tool class. Inside, we define metadata. First one is name. This is the unique ID the LLM uses to call the tool. Keep it lowercase and underscore separated. Second metadata is description. This is actually the most important part for the AI. When the model is thinking, it reads this description to decide, do I need to read a file right now? Yes, this tool does that. The description is very important. Then the schema. We'll be using Zode, and here we define the path validation. The path is the address of the file we want the AI to read. The path can be absolute path. That means full address. It starts from the root of your computer. Relative path starts from your current location. Here, we first specify that the path should be a string, and then with describe function validation, we specifically tell the AI that the path to the file is relative to the project roots. The shape of the input, the .describe function part, is sent to the AI as a hint, telling it exactly what kind of string the path should be. This is an AI engineering best practices for 3 reasons. First, if you move your project from your laptop to a cloud server, the absolute path will change, but the relative path stays exactly the same. Second, safety. If the AI can use absolute paths, a hacker might trick it. Third, token efficiency. A relative path uses fewer tokens than a long absolute path, saving you money on every API call. Great. After setting metadata, we define a function underscore call, which is the executor, where the actual TypeScript logic lives. So first, it takes the argument path, which matches the zoned schema exactly and must return a string. The first task it does is call a helper function called saveReadFile. saveReadFile is the security gate for your project. It decouples the action from the policy. Is it safe? This makes your agentic coding assistant robust enough to run in a production environment where you can't always trust the AI's first guess at a file path. We'll create this inside another folder called safety and inside a file index.ts. This helper takes the path and must return the return type of the function read file. Readfile is a safe, standardized wrapper for reading files. It ensures that any file access is restricted to your project folder and translates messy system errors into clean, readable data that your AI agent can use to self-correct its own mistakes. It takes the file path sent by the AI and returns something that follows the file read result type. Every time the AI tries to read a file, it will return data in this exact shape. It contains success boolean. It tells if the operation worked. Content string. This is the actual text inside the file. It is optional with the question mark. The question mark optional means the field might not exist if success is false. There is no content to return, so we leave it undefined. Error string. The human readable. If the operation is successful, this is undefined. If it fails, we populate this with error messages. Path string, the address of the file. Returning the path back to the AI is a context anchor. It reminds the AI which file it was just looking at, which is helpful if the AI is managing multiple files at once. After setting the return interface, we can now start implementing the read file logic. First, we need to resolve the path using path.resolve. What this means, the agent sends us the file path, which is supposed to be relative. For example, src/utils/logger.ts. With process.cwd function, the current directory, it can be something like /users/engineer/desktop/my-agentic-app. When you run this code, node.js takes the current working directory, appends the relative path you provided, and cleans up any unnecessary dots like dot slash or double dot slash. As a result, we get /users/engineer/desktop/my-agentic-app /soc/utils/logger.ts. Then we do a sanity check to make sure that the resolved path actually exists. If not, return an object with success false. An error message, access denied. The file path. If it succeeds, the agent gets the code it needs to analyze. This is done by calling the readFile function on fx.promises or node.js global object. ReadFile takes the resolved path and the encoding name to decode bits into human readable text. At the end, we return the object with success through no error message and the file path. We can add this logic inside a try catch statement. Then we can go back to the folder safety/indexed.ts and import read file. We can also import save read file if we want. Inside save read file, we are going to call validate file operation. This is a function that checks if a file operation is safe to perform. It takes the operation, it can be read, write, or delete, and the file path. Let's create this function. Here, we are going to add a third argument, context, with type safety context, with default context as the default value. This default context defines the rules of engagement for our file system operations. It uses a defense in depth strategy by combining an allow list with a block list typed as safety context. Safety context has the following properties. Project root string. This uses process.cwd function to pin the home base to the directory where the process started. Allowed paths, an array of string. By setting this to current working directory, we are effectively creating a root jail. The application is forbidden from wandering into other sensitive system areas. Blocked patterns, an array of regular expression. This is a no-fly zone. Even within a project root, these patterns act as high security barriers. We can't perform any action on these folders or files, they are protected. Requires confirmation, Boolean, enables a human in the loop or a second step approval for destructive actions like write or delete. Then we can now define the default context object. For blocked patterns, we want to protect folders like node modules, .env files, the .git folder, the dist folder, and so on. The validate file operation function returns an object that contains safe, boolean, reason, string. Safe tells if the operation is safe, and if not, the reason. In validate file operation, we first create a security sandbox for file system operations called is path allowed. Its job is to make sure that an AI or a script can't escape its intended folder to read sensitive files on your computer. It takes the file path and the context. The context acts as the rulebook. Without it, the code wouldn't know which files are good and which are bad. So its path allowed should return a boolean. If the file path is in the allowed paths array, it returns true. Otherwise, it returns false. Inside is path allowed. We first get the result path because remember the file path is just a relative path, not the full path itself. Once we have this full path, we do a prefix check to ensure that no matter what path the agent provides, it stays physically located inside our project folder. If it starts with the root, the file is inside your project. It returns true. If it does not start with the root, someone is trying to access a file outside, so it returns false. After that, we perform another security check. This is actually a filter. This check makes sure the agent does not look into locked safes. What this means, in our project, there are some safe folders that we define inside blocked patterns. So we create a relative path again, even if we already have file path, because we cannot trust the agent. The agent might send a file path that looks relative but actually escapes your folder. So we compute another relative path using path.relative. It takes the project root and the resolved path and returns a safe relative path. Then we check if this relative path exists, and we go through our list of blocked patterns one by one to check if at least one pattern matches the file path. For example, if we see the words .git in the relative path, it returns true, which triggers the logic and returns false. If it checks the whole list and finds nothing, it skips this and continues. Then even if a path is inside project root, You might want to limit the code to only specific folders. This ensures the file belongs to one of the allowed zones we defined earlier. If something goes wrong, just return false. Now we are done with the isPathAllowed function. Back to validate file operation. If isPathAllowed returns false, we return an object with safe, false, and the reason. Otherwise, we move on and check if the operation is delete. First, we check if the file path exists using the function file exists. It takes the file path and returns an object with exists boolean path string. We get then the full path and we use fs.promises.access to check if the file exists on the hard drive. If the file exists and is readable, the code continues. If the file is missing or locked, it returns exists false. If exists result dot exist is false, we return safe false and the reason why it failed. After that, we create another array, critical files. It contains a list of forbidden files and folders that cannot be deleted, like package.json, packagelog.json, yarn.doc, tsconfiguration.json, readme, and so on. If the agent tries to delete one of these files, it should return false. Next, we check for the write operation. When the agent is trying to save or modify a file, we first get the file extension. If this extension is one of the listed binary extensions, return false. This prevents the agent or a malicious script from writing a virus executable into our project. If the extension is not found, we return true. Now back to save with file. Here, we also check the value of validation.save. If false, return an object with success false and the error description. Otherwise, continue and read the file using read file. Great job! Back to our main tool, read file tool. We can check now the value of results. If false, return an error message. Otherwise, return the file content. Great, we just finished our first tool. We can now add it to the getAgentTools function to make it accessible to our brain. Let's create our second tool, the write file tool. This tool's job is to write content into a file. So every tool has the same structure. We define and export the class extended with LangChain's structured tool, then set metadata like name and description. The description is very important for the agent to know exactly what the tool does. Don't underestimate its power. Then we define the schema validation. Here, we set zone validation for the path. It should be a string, and the describe validation ensures it is a relative path. The content is the text to write. Finally, we define the executor function that contains the tool logic. This function takes the path and the content and returns a string. Inside, we call the guarded write-file function. We'll create this function inside safety/index.ts. This function is about integrity when trying to write content. It takes the file path and the content to add and returns the same type as the write-file function. As with read-file, we are going to create the write-file function. Write-file takes the file path and the content and returns file write results. This interface has success boolean, error optional string, and path string. Then we open a try catch statement and first get the resolved path. If this path does not start with the project root, we block access. Otherwise, we continue. Then we check if each folder inside the resolved path exists before writing. fx.promises.mkd normally throws an error if the folder already exists. But when we add the option recursive through, it changes everything. If the folder already exists, it skips without error. If it does not exist, it creates all necessary folders in the path. For example, if the path is c:/users/u/project/source/index.ts, it will create all missing folders: users, u, desktop, project, and source. Once folders are accessible, we create the file using fs.promises.write_file. It takes resolved path, the content, and the encoding name. If everything goes well, we return success through and the path. Otherwise, we return false. Now back to guarded write file. We import write file. Here, we check if the write operation is legal before touching the hard drive. If the check fails, it blocks the operation and returns a clear explanation. Then we check if the system should pause and ask for human approval before writing. If needs confirmation is undefined, the agent checks global settings to determine if we are in manual or auto mode. So we implement global settings, create a folder called config, and inside it, create a singleton.ts file. Inside, create a function get global settings. This function is a getter for a singleton. It provides a centralized way to access global configuration without creating multiple conflicting versions. It returns settings manager or null. By default, the variable is null. Now we create the settings manager type. In settings.ts. We define an interface settings with version, string, allow list, object of files, comments, array of rules, preferences, object with confirmation mode, manual or auto, and auto confirm non-interactive boolean. Back in singleton.ts, we import settings manager. Then we call get settings function and retrieve the current confirmation mode. Create a variable called settings of type settings and make it accessible only inside this class using the private keywords. Then we are going to give this variable a default value when the settings class is created. And for that, we will use the constructor method. This is the first method that is called when a class is created. Inside the constructor, I'm going to pass an optional project root string and create a root variable that represents the given project root or falls back to the current folder. Then we set the value of settings using this dot settings to the value of the constant default settings. This is your default configuration object. It defines the initial state of your app's settings before anything is loaded from a file. Version 1.0.0 tracks your config version, useful when you later migrate settings or detect outdated configurations. Allow list. This is a security control layer. Which files the agent can access. Commands, which CLI commands are allowed. Preferences, confirmation mode. Manual, the system will ask before performing actions. Auto confirm non-interactive true if running in non-interactive mode like a script. It skips prompts, automatically approves actions. Then we are going to create a getter function that allows us to access the settings data from outside the class securely. After that, we can import and use get settings where needed. If it is null or undefined, we default to manual. We compare the mode to manual and store the resulting needs confirmation. If needs confirmation is true, we call request confirmation. This function defines how the app asks the user for permission before doing something dangerous. It takes operation, write, delete, execute. Target, string, details, optional context. It returns a promise with approved boolean, remember optional boolean. Inside, we first get default settings. If settings exist, and if the operation is executed, we call is command allowed. Otherwise, we call is file allowed. Is command allowed checks if a command is in the allowed list and returns a boolean. Is fire allowed? Checks fire rules and returns a boolean. If allowed, we return approved true. If no interaction is possible, like CI/CD or scripts, we detect the environment using process.stdin.isTty. If false, the input is being piped from another program or file, meaning the code cannot ask for permission because no one is watching the screen. Then, when it is true, I get the default settings and the value of auto-confirm non-interactive. I check if the execute operation is already allowed. When no human is available, the code relies on a strict by default policy. It will only return approved true if one of two conditions is met. The target is already pre-approved via is command allowed. or is file allowed. The user has explicitly turned on or trust everything in background mode flag. If neither is true, the operation is rejected because the system refuses to guess whether a dangerous operation is safe. If the operation is blocked, the code logs a detailed message explaining why and how to fix it. This is great developer experience because it prevents the silent failure trap. After handling non-interactive mode, we switch to interactive mode. Here we define how the system behaves when a human is present, but auto mode is enabled. First, I get the confirmation mode is auto. I inform the developer or user that the system is currently operating under auto approval. Then I get the target type. Either command, execution, or file operation. Then I define the yes and no variables. These are used to initialize the inquirer select prompt, which is the interactive menu the user sees in the terminal. The select component comes from the inquirer package. Install it, then import the select component. Name confirm. This is the internal key used to retrieve the answer once the user presses enter. Message uses a template literal to dynamically tell the user what they are approving. Choices passes the array of options. Yes, choice, yes, remember choice, and no choice. Once the menu is created, I print it to the terminal. And run prompt.run function. The user sees the options and must select one. If the answer is yes, I return approved through. If the answer is yes, remember choice. I first add the target to the allow list so the user doesn't need to validate it again. Using add command to allow list. This function is the persistent layer for our security system. It handles the remember me logic by taking a command that was manually approved and permanently recording it. Before adding anything, it uses .sum function to check if the command is already in the list. If it is, the function returns early to prevent duplication. Then it saves the command as an object with a timestamp added at. Setting this .30 through signals that the in-memory data has changed compared to what's on disk. Finally, it calls await this.save function. This function is the reliability layer of our settings system. It uses an atomic write strategy to prevent corruption. It first checks if that this.dirty is null and exits early if nothing changed. Then it calls ensure directory. Ensure directory ensures that the folder structure exists before saving. Without this, save function would crash if the folder didn't exist. It first performs a quick check to see if the folder exists. Setting path is a private string property pointing to settings.local.json. In the constructor, we set its value using path.resolve. The app uses the root variable and path.resolve to calculate the absolute path for the settings file. Then comes the atomic write process. It writes to a temporary file instead of directly to settings.json. If the program crashes, the original file remains intact. Once writing succeeds, it renames the temp file. This operation is atomic, meaning the replacement happens instantly. Only after success, it sets this.dirty to false. If something goes wrong, it logs the error and throws it. Back to request confirmation. If the operation is not a command execution, we call add file to allow list. This function records approved file actions into the allow list It works similarly to add comment to allow list, but it is context aware. It stores both the file path and the operation. It uses .sum function to avoid duplicates. Then pushes a new object with path operation date.now. Then it sets this .dirty to true and calls await this save function. Once done, we log the results and return approved through. If the answer is no, we return approved false. If something goes wrong, we also return approved false. Back to names confirmation logic. If approved is false, we return success false. Otherwise, we call write file function and pass to it file path and content. We are now done with coded write file and write file tool. In write file tool, we import coded write file. If result.success is false, return an error message. Otherwise, return a success message. Then we add this tool to the Get Agent Tools array. Next tool is List Files tool. Same pattern as the others. Set metadata name, description, schema. and executor function. The function receives an object containing a path. If the AI doesn't specify a folder, it defaults to dot. That means project root. Then we create the helper function list files. This function is the low-level engine that powers list files tool. It returns success boolean, an array of file info, error optional string. File info has name, path is directory, size, and modified. First, we set a security syntax by checking if the resolved path is outside the project root. Then we read the directory using fs.promises.readD. With file types true. This allows us to know if each entry is a file or folder. Then we gather metadata in parallel using promise.all. Instead of processing files one by one, we run all start calls simultaneously. Then we normalize paths. Instead of returning long absolute paths, we convert them into clean relative paths like soc/index.ts. At the end, we return success, true, and false. If it fails, return success false and error.message. Back to list files tool. If result.success is false, return an error. If files is empty, return directory is empty. Otherwise, we format the output. If file dot is directory, use the directory icon. Otherwise, use the file icon. If size exists, include it. Otherwise, leave it empty. We construct each line like icon, file.path, and size. Then use .join function to combine all lines into a single string. Finally, return the results. Add this tool to Agent Tools. Next tool is File Exist tool. Next tool is File Exist tool. This tool provides a lightweight way to verify if a file or a directory exists. Same structure as others. The executor calls file exists. File exists resolves the path. Uses fs.promises.access. If the file exists, it returns exists through and the path. If not, it caches error and return exists false. Then add this tool to Agent Tools. Next tool is Delete File tool. This is the same pattern. In the executor, we use save delete file. Save delete file is the security gatekeeper for file deletion. Unlike a normal delete, it performs safety checks before removing a file. This function, delete file, is the low-level execution engine as delete removing files from the disk, while save delete file acts as the security guard. This function handles the actual interaction with the operating system, ensuring the operation is precise and restricts to files only. Let's implement it step by step. First step, path resolution and sandbox check. Similar to your older tools, it uses path.resolve to find the absolute path and immediately verifies it. Starts with process.cwd function. Second step, the file and directory guard. Before deleting the code, checks the metadata. If the path points to a directory rather than a file, it refuses to proceed. This is a safety feature to prevent accidental recursive deletions of entire folders when only a single file was targeted. Third step, the unlink command. The actual deleting happens via fs.promises.unlink. In Unix and Node.js terms, unlinking a file is the standard way to remove its name from the file system, effectively deleting it. The catch block ensures that if the file is already gone, or if the OS locks the file, the program returns a clean success false object instead of crashing the entire runtime. Then back to save delete file. We will implement this function step by step. The first step, the validation call. Before touching the hard drive, it calls validate file operation. This is a specialized function that checks for illegal files outside the project root, protected files, trying to delete poor configuration files or read-only resources, system folders, ensuring the path is not a critical system directory. If validation.safe is false, the function stops immediately. It returns a standardized error object that explains exactly why the safety violation occurred. This prevents the real delete file function from ever running. The final step will return delete file only if the validation returns a green light. Back to delete file tool, we import safe delete file. If result.success is false, return the error message. If true, return a successful message. We are done with this tool. Add it to the agent tools array. Next tool is search files tool. This tool allows the agent to look inside every file simultaneously to find specific logic, bugs, or patterns. This tool has a name and a description. Then the schema. It supports more than just a simple keyword search. We have pattern. It supports both plain text and regular expressions, allowing complex searches. Example, finding all functions that start with of. File pattern. It acts as a filter, so the system doesn't waste time searching compiled JavaScript images or node modules. Case sensitive. This is a toggle for precision, useful when searching for class names or variable names. Then the executor function. The underscore call function transforms raw search data into a grep style report. First, we call search files. This function is the orchestration logic for the entire search system. It transforms a user's search string into a precise scanning operation, handles the transition between plain text and regular expression, and manages performance limits. It takes options typed as search options. This type has pattern, string, path, optional string, file pattern, optional string, case sensitive, optional boolean. Line number, optional number, max results, optional number. Include binary, optional boolean. The function returns a promise of search result array. The search result includes file string, lion number, column number, match string, context string. Now let's implement its logic step by step. First step, we destructure the options and get variables like pattern, path, and so on. If pattern is null, we throw an error. Second step, this is defensive programming. We attempt to treat the pattern as a regular expression. If it is valid, use it as it is. If it is invalid, escape special characters instead of crashing. Third step, The function breaks the task into stages. Get files to search. This function acts as a file crawler. Its job is to navigate the project structure and select relevant files. We define an inner function, work, that calls itself when it finds a folder. Deep traversal into subfolders like src/components/buttons. To keep the search fast, we skip folders starting with dot, like .git, skip node modules, and skip dist. If a file pattern is provided, asterisk replaced with dot asterisk, question mark replaced with dot, then we test each file name against this regular expression. Back to search files. We loop through every file found and call search in file. This function, search in file, is the microscope of the system. While the worker finds files, this function opens each file and scans line by line. It takes file path, string, pattern, regular expression, options, search options, and returns an array of search results. It gets the content of the file using read file. This function, read file, is the input port for your entire system. It is the fundamental utility that allows the AI and the tools to pull text from your hard drive into the application's memory while enforcing strict security boundaries. It takes the file path and returns file read results. Now, let's implement the core logic of the search in file function. First step, instead of searching the entire file as one giant block of text, the function splits the content into an array using content.split. Why? This allows the tool to provide context. By knowing which index it is currently on, it can accurately report the line number and return the specific string of code where the match was found. Second, the use of match all is important for precision. If a line contains the same pattern twice, this logic ensures every instance is recorded with its unique column position, not just the first one. For every match found, the function builds a detailed search result object. It maps the 0-based index to 1-based human-readable numbers. It captures line.trim function, providing a clean preview of the code so the user doesn't have to open the file. At the end, we return results. Then back to the search files function. In a massive project with thousands of files, a common search term could return tens of thousands of results. By breaking the loop as soon as the max results threshold is hit, the system remains fast and prevents the AI from being overwhelmed by a wall of text. At the end, we return all results. Here, we may need to add undefined to this property and also import the search files function and fix some type errors. Back to search file tool. If result.length is 0, return no matches found for a pattern. Otherwise, we iterate through the results array. For every match found, we build our string using our standardized template. This follows the industry standard grep format, allowing the AI to know exactly where the match is located. Or.context shows the actual line of code where the match occurred. I also add a visual pointer. This adds a second line for every result using a branch character to highlight the specific text that triggered the match. Once every result is turned into a formatted string, dot join stacks them vertically, making them easy to read in a terminal. The final return statement adds a header. Found results.length matches. This gives the user an immediate sense of scale before diving into the details. We are done with search file tool. Let's add it to the agent tools array. Next tool is edit file tool. Same pattern as other tools. We are going to define name, description, and schema. This schema requires both old string and new string. Then the executor function. It takes path, old string, new string, and returns a string. Then we call a replace text function. This function acts like a search and replace robot that only touches specific lines, making it safer and more efficient. All edit functions will stay in the file edit with diff. Here we define replace text. It takes path, old text, new text, occurrence. It returns edit result. Edit result contains success boolean. File path string, operation string, diff optional string, message string, backup created optional boolean. Hanks applied optional number. It first calls your read file utility to load the file into memory. If the file doesn't exist, is binary, or is locked, it stops and returns a structured failure object. Before making any changes, it checks if old text exists in the file. If not, it errors out. This prevents hallucinated edits. It splits the file into lines. Then it loops through them. If a specific occurrence is requested, it waits until the count matches. If occurrence is -1, it replaces the last occurrence. Then it stops to avoid unnecessary changes. It joins the lines back together and generates a diff using generate diff. This function, generate diff, is the evidence collector of your system. It creates a visual record of changes, similar to Git. It takes file name, original, modified, context lines, and returns diff results. It uses a path creator to compare versions. Context lines ensures surrounding lines are included. It returns a structured object, not just a string. Back to replace text, we import generate diff, then call guarded write file. These triggers allow list checks, human confirmation, automatic backup. Finally, it returns a full report, including the diff and confirmation of backup. If something fails, return success false. Back to agent tools. Import replace text. If result.success is false, return error editing file. Otherwise, display the message with result.def. Let's add this tool to the agent tools array. Next tool is execute command tool. It has same pattern. Then the executor takes a command string and returns a string. We are going to call coded execute command. This function handles commands like npm install. It acts as a checkpoint before execution. It takes command string, require confirmation optional boolean, and returns the result of execute command. Now let's create execute command inside terminal.ts. It returns terminal results. This has success boolean stdout, optional string, stderror, optional string, error, string, optional string, comment, string, exit code, optional number. First, we call is command safe. This function is the firewall for terminal commands. First step, we are going to convert to lowercase and trim spaces. Then, check against forbidden patterns like OM- OF or format. If found, it blocks immediately. Next step, we are going to prevent command chaining tricks. For example, save command plus hidden malicious one. After that, only allow predefined commands like npm get ls approved. Anything else is blocked. Then we return safe true if all checks pass. Back to execute command. If safe is false, return failure. Otherwise, execute inside project root. We use promisify with exec from child process. This converts callback-based functions into promises. Then we kill command after 30 seconds. Limit output to 1 megabyte. Capture std out and std error. If it fails, return error information including exit code. Back to guarded execute command. This determines the mode. It can be manual or auto. If confirmation is required, prompt the user. If user cancels the confirmation, just return operation cancelled. Finally, if approved, call execute command. Back to execute command tool. If result.success is false, return error. Otherwise, return std out, std error, or success message. We are done with this tool. Let's add it to agent tools. Great job! We now created all the tools our agent needs to perform user instructions. Next step is to integrate these tools into the agent and build the memory layer. Now, go to the agent folder and open agent.ts. Inside, the run agent function. At the beginning of the try catch block, we are going to add tools to our agent. First, we dynamically load the module located at tools/agenttools.js using import. This happens at runtime and returns a promise. Once that is done, we call the getAgentTools function that we just imported. Next, we define a helper function called random. This function takes an array of strings and returns some random element from it. After that, we create an object called color map. This object maps color names like cyan or green to formatting functions from the chalk library. Each value in this object is a function that styles terminal text in a specific color. This makes it easy to dynamically choose colors when printing output. Then we define an array of status messages called messages list. This array contains different strings that indicate progress or activity. We can combine this with our random function to display a different message each time, which adds some variation to the output. Next, we pick up random key from the color map object. We do this by calling object.keys function to get all the keys, then passing that array into the random function. The as key of type of color map port is a TypeScript assertion that tells the compiler the result will always be a valid key of color map. After that, we generate a styled message. We select our random message from messages list, then apply a color function from color map using the randomly selected color. Now we create and start a spinner using the Aura library. We configure the spinner with the colored text or randomly selected spinner style from spinner types and the chosen color. Spinner types is simply an array of supported spinner styles like dots, line, arc, and more. As any assertions are used here to bypass strict TypeScript checks for the spinner typing color. Finally, calling start function begins the animated spinner in the terminal, giving visual feedback that something is in progress. Next, we transform the tools array into a formatted string description. We do this using .map function to loop over each tool and convert it into a readable line. After that, we create the system prompt. A system prompt is a special instruction given to an AI model at the very start of a conversation. It defines how the model should behave, think, and respond. In simple terms, it sets the role, rules, and context for the AI. For example, who it is. You are a senior software engineer assistant. What it does, you help with coding tasks by reading, writing, and modifying files safely. It also defines what the AI is allowed to do. In our case, we want the AI to use tools to execute tasks. We place the system prompt inside a template string so we can inject variables like tools desk. Our system prompt also defines how the model should respond, including format and style. Here we use a format called React. React stands for reasoning and acting. It's a method that makes AI agents behave like thinking assistants that can use tools step by step. Here is how it works. First, the model reasons. It explains what it is thinking and what it needs to do. For example, I need to inspect the project structure. Second, it acts by using a tool. For example, list underscore files. Third, it provides the input parameters for that tool. This is usually a JSON object like this. We have the path keyword and dot as value. This object defines two things: the key path, which is the input parameter name, and the value dot, which refers to the current directory. And the last step in the React loop is the observation. And the last step in the React loop is the observation. This is when the tool returns an output, and the model uses that result to continue its reasoning. But in our case, we don't need to include observation in the prompt. Why? Because observation is not written by the model in advance. It is injected by your runtime system after the tool executes. Great, now we have our first output format that we want the AI to follow. But we are also going to define another format called XML. So why do we support multiple output formats? Because LLMs are not deterministic. They don't always reliably follow a single strict syntax. By giving multiple valid formats, we increase reliability. If the model struggles with one format, it can fall back to the other. This gives us better compatibility across different AI models. Now, let's talk about the XML format. This is a structured way of calling a tool using XML like tags instead of JSON or React style. First, we identify which tool to execute. Function means this is a tool call. List underscore files is the exact name of the tool to execute. We define it this way because the system needs a clear identifier before it knows what to run. This format is designed for machine parsing, not human readability. The system can easily extract the function name and all required parameters inside the parameters tag. So instead of guessing intent, the system directly reads exactly what function to call. Now that we have defined the formats, the last part of the system prompt is the guidelines. The guidelines section defines the rules the AI must follow when using tools. Think of them as behavior rules. What the AI should do, safety constraints, what it should avoid, consistency rules, how it should act. Without guidelines, the AI might skip important checks, use the wrong tools, overwrite files accidentally, behave unpredictably. So we define clear rules like always read files before modifying them. Use write file to create or update files. Use list files to explore directories. Use delete file carefully. Finally, we add begin as a trigger. This tells the model the instructions are finished. Now start responding. Now the system prompt is ready. Next, we create a variable called messages. This variable stores the conversation history between the user and the assistant. It's an array where each item is an object with two fields, role and content. We start by creating a fresh conversation payload to send to the AI. The first message is the system instruction. Role system defines the rules. Content system prompt defines all the instructions we just built. This tells the AI, you are a coding assistant with these tools and rules. The second message represents the user's input. Role, user, the human request. Content, user input, whatever the user typed. Now the AI has context, instructions, and a task. Next, we start a for loop. This loop allows us to repeat the agent's reasoning process multiple times. It runs up to maximum iterations, which default to 5. That means the agent can think and act up to 5 steps before stopping. For a better user experience, we log progress to the console. Each time the agent loops, the iteration count increases. Then we send the messages array to the LLM using await LLM.invoke function. The model returns a response that includes both text and metadata. We extract only the text content, wrap it with string function to ensure it is a string, and use .trim function to remove extra white space. Now we check the response. Does this output contain a tool call? If it is neither an XML tool call nor a React tool call, then it is just a normal response, and we return it immediately. If it does contain a tool call, we pass the content to a function called post_tool_call. This function converts raw LLM text into a structured object. It supports both formats, React and XML. It takes a string as input and returns either a tool call object, tool name input, or null if nothing is found. We start with the React format. Using a regular expression, we extract the tool name from action, the JSON input from input, if found, we pause the JSON and return our structured results. If parsing fails, we log the error and move to XML parsing. For XML, we use another regular expression to detect the function call. If there is no match, it is not a tool call. If there is, we extract the tool name and the inner content. Then we create an empty object for parameters. We use another regular expression to extract parameter blocks. Inside a loop, we extract the parameter name, extract the value, try to parse it as JSON. If parsing fails, we keep it as a string. Finally, return object that contains the tool name and the input. Back in run agent, we check if a valid tool call was found. If not, we return the raw output. If yes, we extract the tool name and input. Next, we normalize parameters. If file path exists, we copy it into path. If path is not already set, if directory exists, we also map it to path. Then we look for the matching tool in our tools list. If no tool is found, we store the assistance response and add an error message. This allows the model to correct itself in the next iteration. If the tool exists, we store the result as a string and handle any errors such as file not found and permission issues. We also check if the operation was intentionally cancelled by the user. If so, we return operation cancelled by user. If the loop reaches maximum iterations, we stop the agent and return our message. And very important, we stop the spinner at the end, otherwise it will keep spinning forever in the terminal. At this point, we have successfully added tools to our agent. That is the hardest part. From here, making the agent more intelligent is less about adding tools and more about improving control, memory, and decision quality. So next, we introduce our memory layer. At the root of the project, create a folder called memory. And inside it, create a file history.ts. This file is responsible for storing past interactions like messages, tool calls, and results. This allows the agent to reuse context later. To keep things clean and scalable, we create a history manager class. This class uses an internal storage system based on a session store. Now we need to create that session store in the same folder. Create session.store.ts. This class handles saving sessions, loading sessions, organizing memory on disk. It has several properties. Base path, the root directory for all memory, session path, the folder where sessions are stored, indexed path, a file that tracks session metadata, index write queue, or queue to control async writes. In the constructor, we initialize everything. It takes a configuration object with a storage path. We resolve it into an absolute path using process.cwd function and path.resolve function. Then we build the section folder path using path.join function. And the index file path. index.json. Finally, we create an initialize function. This function prepares the storage system before use. It creates the sessions directory with object recursive true. That means it creates missing parent folders and won't crash if the folder already exists. We are going to create the load session function. This is an asynchronous function that loads a saved session from disk using a session ID. It takes a session ID as input and returns either a session object or null if the section cannot be found or loaded. Inside the function, we first build the full file path to the section file. Then we read the file from disk as a string using fsp.read file. After that, we convert the JSON string into a real JavaScript object. If anything goes wrong during this process, we simply return null. Now we need to define some types. Create a file called types.ts. First, we define the session interface. This describes the exact structure of a saved agent session. It includes ID or unique identifier for the session, name, an optional string created at or timestamp for when the session was created, updated at another timestamp, usually another timestamp updated over time. Messages, an array of message objects. Next, we define the message interface. Each message has role and content. The role uses a type called message role. Message role is a TypeScript union type. It restricts the role to only 4 possible values. System instructions for the AI. User input from the user. Assistant response from the AI. Tool output from a tool. Now we extend the session interface by adding an actions field. This field stores what the agent actually did. For example, which tool was used, the input, the output, the date, the duration, and whether the operation succeeded. We also add a metadata field to the session. This is used to store extra context about how the agent operates, not the conversation itself. It can include the model name, total iterations, how many steps the agent has taken, tags to categorize the session, project root, which is the working directory, and a plan, which is a structured step-by-step plan created by the agent. For now, we can leave most of this empty. We will also add an optional current step field to track progress. Now back to the session file. Inside load session, instead of returning raw data, we return the serialized session. This function takes the raw JSON data and converts it into a valid session object. So let's create the serialized session. This function takes raw data from storage, validates it, and safely converts it into a session. The input contains data.session, the actual session object, data.version, the format version. The function returns either a valid session or a null if something is wrong. It performs a few checks. If data.section.id is missing, it means it is invalid. If data.session.messages is not an array, it means it is also invalid. If either condition fails, we discard the data. If everything is valid, we return the session as it is. And if anything unexpected happens, we safely return null. Great, that covers sessions. Now let's go back to the history manager. We are going to add a new private property called config. This is a fully initialized configuration object for the class. It uses the memory config type but excludes the enable vector store fields. Let's define memory config. This represents all configuration options for the memory system. It includes storage path. This is where memory is stored on disk. Maximum messages per session. Optional. This limits how many messages a session can store. Autosave. Optional. This determines whether sessions are saved automatically. Enable vector store. Optional. This enables advanced memory like embeddings or a vector database. Except for a storage path, everything is optional. In a class, we also define enable vector store as a boolean. This acts as a feature flag. For now, we only use session files for memory. Later, we can enable vector storage for long-term memory. Next, we add a cache property. This is an in-memory cache using a map function. It stores key, the session ID, value, the session object. This allows fast access to sessions without hitting the disk. We also define current session ID. This tracks which session the agent is currently working on. Next is dirty. This is a set that stores session IDs with unsaved changes. It helps us track which sessions need to be written to disk. Then we have access order. This is an array of session IDs that tracks usage orders. We also define maximum cached sessions. This is a number that limits how many sessions we keep in memory. By default, we store up to 10 sessions. Next is save queue. This is a per session save log system. It is implemented as a map. It has key, the session ID, value, the current save operation or null. This prevents multiple writes from happening at the same time for the same session. Now we initialize these properties in the constructor. The constructor takes an options object of type history manager options. History manager options defines what can be passed when creating a history manager. It includes config and optional objects. We use partial memory config, which makes all fields optional. Then we initialize this.config. We start with default memory config and override it with any values from options.config. Default memory config defines the default settings for the memory system. It uses strong TypeScript typing to ensure everything is valid. And for now, we temporarily exclude enable vector store from strict enforcement. We now extend the configuration by introducing a new flag enabled vector store typed as a boolean. Default underscore memory underscore config is defined as an object with the following values: storage path, dot AI coding agent slash memory, maximum messages per session 1000, auto save through, enable vector store false. Next, this dot store is an instance of session store. This is responsible for handling all session persistence on disk. We also define this dot maximum cached sessions, which limits in-memory caching to 10 sessions. After initialization, we implement the getCurrent session function. This function returns the currently active session. If none exists, it creates a new one. So first, it checks if a session is currently active. If a session exists, it tries to load it. If the session is found in cache, we return a copy of it, not the original. This prevents accidental mutation of cached memory. If the session is not in cache, we continue by loading it from disk. We read the session from the file system. If the session is found, we store it in cache for faster future access and return a copy. If the session is missing, we treat it as if no session exists. And if no session exists at all, we automatically create a fresh session. To do that, we use the create session function. This function creates a brand new session and optionally accepts a name and a project root. Inside this helper, we create a new session object. We capture the current time in milliseconds, which is used for created ads and updated ads. We then generate a unique session ID using crypto random UUID function. This ensures every section has a globally unique identifier. The session object includes ID, unique identifier, name, session label, created at, creation timestamp, updated at, last modification time, messages, empty conversation history, actions, empty action log, metadata, context about the session. We also update the session interface so that name can be undefined. Back in create session, we import and use this helper. We then store the session in memory using set cache so it can be accessed quickly without disk reads. Next, we mark it as the current session. This .current session ID equals to session.id. This means all future operations will belong to this session. We then mark the session as dirty. This indicates this session has unsaved changes and must be persisted later. If autosave is enabled, we trigger save async, which runs in the background. Save async is a private method that saves a session without blocking execution. First, it checks, is a save already running for this session? If yes, it reuses the existing save operation. Otherwise, it calls save now. Save now performs the actual disk write. It first retrieves the session from the in-memory cache. If the session does not exist, it exits immediately. If it exists, it passes the session to session_store.saveSession function. This function is responsible for writing the session to disk permanently. Inside save session, we first ensure the storage system is initialized. We then build file paths using sessions path, session ID, and .json. We also create a temporary file for safe writes. A backup file for recovery. These two files are essential for data safety. Temp file prevents partial writes, and backup file allows recovery if something fails. Next, we serialize the session using JSON.stringify. This converts the session into a JSON string. The serialized session function wraps the session and copies all session data, updates at. Attaches a version number for schema tracking. We then continue with save file writing. If the file already exists, we create a backup using fsp.copy file. We ensure directories exist using fsp.mkd. We write data to a temporary file using fsp.writefile. Then we attempt an atomic replace using fsp.rename. On some systems, especially Windows, rename may fail. If that happens with errors like exists, xdev, we fall back to manual copying the file and deleting the temporary file. After saving, we update the session registry using update index. Update index updates the session index file with metadata. It loads all sessions using list sessions. List sessions returns all session summaries from index.json. Each session summary contains ID, name, timestamp, message count, action count, project root. Inside list sessions, we load index.json. Pause it and return all sessions if valid. If something fails, we rebuild the index using rebuild index. Rebuild index is a self-healing system. It reconstructs the index from actual session files using many steps. The first one is by reading session directory using fsp.readday. Then filter valid session files. convert them to full paths, load each session file, pause and deserialize sessions, build summary updates, sort by latest update, and finally save back to index. We then persist the index using write indexed queues. This ensures writes are executed sequentially. Write index writes the index safely. It creates temporary file, writes data, tries atomic rename, If rename fails due to permission errors or cross-device issues, or file conflicts, we fall back to manual copy and cleanup. Back in save async function, we also handle errors safely. In the finally block, we remove the session from save queue. We also store the latest save promise per session. Then we return the save promise. Back in create session, here we are going to return the session object. Then implement switch session. This function loads the session from disk. Validates it exists. Sets it as active. catches it, and returns a safe copy. If the session does not exist, we stop execution immediately. Now we are going to implement add message. This function appends a message to the active session. We first define the message structure. It has role, content, timestamp, optional tool called ID, and optional tool name. Inside add message, we get the active session. Build a complete message object. Add it to the session. Enforce maximum message limit. Trim old messages if needed. Update cache. Mark session as dirty, and then trigger autosave if enabled. Next is add action. This function records what the agent actually did. An action includes ID, tool name, input, output, timestamp, duration, success flag, and optional error. Inside add action, we get first active session, build action object, append it, update timestamp, increment iteration counter, update cache, mark it as dirty, and trigger autosave. The next function is get recent messages. This function returns the last n messages. The default one is 10. It checks if session exists. Reads from cache. Slices recent messages. And returns saved copies. Finally, we have function get all messages. This returns the full message history. It checks active session. Reads from cache. Returns empty array if missing. Otherwise, returns all messages safely. Next, we transform every message by iterating through the full message list and normalizing it. The important part here is legacy migration handling. When a message has the role tool, we normalize it. We convert its structure using a semantic transformation. The role tool becomes user. The raw content becomes observation. And the tool name is preserved. At the end, we return a shallow copy of the messages to protect the internal cache from accidental mutations. Now we create get session preview. This function acts as a lightweight session preview fetcher. It takes a session ID and returns either a session summary or a null. First, it checks if the requested session is the current session. If it is, we load it directly from the cache layer. Then we build a summary object from it. If the session is not the current session, we delegate the work to this.store.getSessionPreview. So let's create that function inside the section store class. Get session preview takes a session ID and returns a session summary or null. It first loads all session previews. Then it searches for the matching session. It loops through the list and stops immediately when it finds a match. Next, we define list sessions. This function is responsible for retrieving all sessions from disk or database. In contrast, get current session ID only returns the ID of the currently active session. We also implement save current session. This function explicitly saves the current session. If no session exists, it simply exits. Next is rename current session. This function renames the active section in memory. It takes a new session name and returns the updated session or null. First, it ensures there is an active session. Then it retrieves it from cache. It applies the new name, marks the session as dirty. And saves it if autosave is enabled. Now load session. This function loads the session from the store using its session ID and returns either the session or null. It delegates to this.store load session. We also define get store, which returns the internal storage engine used by the session manager. Next, we implement mock clean. This function marks a session as having no unsaved changes. It does this by removing the session ID from the dirty set. Then we create flush. This function forces all dirty sessions to be saved immediately, one by one. It works by taking a snapshot of all dirty sessions iterating through them sequentially and saving each one synchronously. Now we can create a new file called singleton.ts. This file provides a singleton accessor for the history manager. It ensures only one shared instance exists across the entire application. We define our global variable, global memory, typed as history manager, which can also be null by default. Then we create set global memory function that takes the memory. This stores the instance globally, and then get global memory function. This retrieves it from anywhere in the application. Next, we can create vector.store.ts. This file is responsible for embedding and semantic search capabilities. It represents a storage layer for vector embeddings. For now, we implement a simple in-memory keyword-based search. We create an in-memory vector store class that implements vector store. The vector store interface defines add text that stores a piece of text. We define a vector document interface containing ID, content, embedding, and metadata. Search that retrieves relevant documents. And clear that resets storage. Now we are going to implement the class. We start with a private document array that holds all stored items. The first function is add text. This function takes a piece of text, wraps it into a document, and stores it in memory. Right now, we simply push it into the array. Later, we will replace this with real embedding generation. The next function is search. This function finds documents whose content matches the query string. It normalizes the query, scans all documents, matches using simple substring logic, applies a result limit. Later, this will become semantic similarity search using embeddings. The next function is clear. This function deletes everything in memory by resetting the array. Get document count. This returns how many documents are currently stored. Now we centralize everything in index.ts by importing all types like session store, history manager, in-memory vector store, and vector-related interfaces. Great! Now the memory system is complete. It is time to integrate it into the agent. We open agent.ts and add a new optional argument, memory, typed as history manager. Now we update message initialization logic. We introduce two modes, persistent memory mode and stateless mode. If memory exists, we get the current session. Check existing messages. If there are no messages, we treat it as the first interaction. And create a system message. If messages already exist, we store the user input and load full conversation history then formatted for the LLM. Inside the iteration loop, if the model does not request a tool, we store the assisted response in memory. And persist it if memory is enabled. Now we create message. Inside types.ts, this function builds a message object with role, content, timestamp, optional tool call ID, optional tool name, we also update the message interface to include tool call ID and tool name. Back in agent.ts, we now call save current session to persist state. Next, after handling cancellation logic, we introduce create action. This records tool execution events into memory. It takes tool name, input, output, success flag, We define create action in types.ts returning an action object containing the ID, tool name, input, output, timestamp, duration, success, and error. We also make some fields optional in the action interface. Back in agent.ts, we import create action, store assistant message, store tool outputs as an observation. At the end of the iteration loop, we save the session before returning a maximum iteration reached message. Now we move to CLI.ts. At startup, we initialize the memory system using environment configuration. This configuration has storage path. Maximum messages per session. And autosave enabled. We store this instance globally using set global memory. Then we parse CLI arguments and combine them into a single input string. We wrap execution in a try-catch block and show a loading spinner. If an error occurs, we display it in the terminal. If no input is provided, we clear the terminal, load the correct session, and render the dashboard. Now we are going to implement render dashboard. This function starts the interactive CLI UI, loads memory and session states, and displays our live interface. We calculate terminal dimensions: width, content width, left panel width, right panel width. We also define constants: minimum terminal width, minimum panel width, and spacing between panels. Then we built the UI step by step. First one is header. We implement render headers. This function builds a responsive CLI header. It supports wide terminal mode, that is full banner. compact mode, that is single line header. We also implement center text for alignment and divider for horizontal separators. Then we built the left panel. It displays system information like model, version, current directory, and timestamp. The right panel shows quick actions, available commands, session-aware information. The footer renders a separator line user instructions. We merge everything using merge panels row. This function aligns left and right panels row by row. We also implement fate to with, which truncates long strings. Finally, we wrap everything using boxing to render a framed CLI interface. At this point, the dashboard is fully complete. Now, we add a safety layer by implementing show trust check, which asks the user to confirm trusting the project directory before allowing file operations. It clears the terminal, displays a warning, prompts user confirmation using inquirer. If the user selects no, the program exits immediately. After that, we initialize environment variables using ensure config. This function loads .env file detects missing keys. prompts the user for required values. Writes them back automatically and reloads configuration. We use .env for environment loading and readline for input handling. Finally, we implement this is the core runtime of the CLI agent. It continuously prompts the user, processes input, executes commands or AI responses, and repeats until exit. We handle control plus C exit, empty input, command normalization, slash commands, AI execution flow. Also implement handle command, which routes CLI commands. For example, /init initializes project configuration and checks for AI coding agent.md file, and also prepares project context. If the file already exists, we warn the user and suggest editing it instead. If it does not exist, we create a default project AI context file using create context template. This function creates a default context file for the AI agent and returns success, whether the file was created, path, where it was created. First, it checks if the file already exists. If it does, it returns success false along with the file path. Otherwise, it creates the file and initializes it with a template. This template represents the main AI context that will be loaded into every user prompt. Now back in the main function, we continue execution. We check the result. If result.success is true, we display a success message in the terminal. Otherwise, we inform the user that the file already exists. Next command is /restore session. This command restores the last conversation history. First, we retrieve all active sessions. For this, we need a new function in the session store class. This function is similar to list sessions, but it only returns sessions where message count is greater than 0. Back in handle command, if no sessions are found, we return immediately. Otherwise, we take the first session and compare correct session ID and latest session ID. If they are the same, we simply return we are already in the latest session. If not, we switch sessions using switch session function. We wrap this in a condition to avoid TypeScript errors. After switching, we clear the console and re-render the dashboard. To avoid repeating logic like check latest session everywhere, we centralize this logic earlier in the flow. Next, after restoring our session, we print a readable summary in the terminal. We format the timestamp updated at into a human readable date, the session name, message count, and update type. This gives the user a clear overview of what was restored. At this point, command handling is complete. We can always extend it later with additional features like planning mode, cost tracking, advanced agent controls. By default, if a command is not recognized, we return just an unknown command. Now we move back to the core loop running the AI agent. This is the main intelligence system. We set maximum iterations at 100 to control cost and prevent infinite loops. We then print the result to the terminal, including spacing for readability. Finally, we add error handling. If anything breaks during execution, we fail silently and exit cleanly. Now the agent system is complete. It is time to test it. Let's run npm run dev. We hit an ES module error. The issue is that we use require instead of import. We fixed this by switching everything to ES module syntax. Let's try again. Now the trust gate appears correctly. If we select no, the process stops. If we select yes, we proceed. Next, we can build the project using npm run build. Then link it globally by running the command npm link. This allows us to use the CLI anywhere on the system like our global package. Before that, we must ensure package.json includes our bin configuration. This maps our terminal command to our CLI entry file. We define AI coding agent as CLI name that points to directory dist CLI. After rebuilding and linking again, we test in another folder. Let's run AI coding agent. It doesn't work. The issue is that the CLI entry file is not executable. We fix this by adding this at the top of the file index.ts in CLI folder. This tells the system, run this file using node.js. Let's rebuild the project and link again. Now everything works. We can run the agent again. Let's configure environment variables first. Set your OpenRouter API key. Then your module name. You can start with a free module. After setting up, we can see the agent dashboard. And here, let's write hello. And the agent responds correctly. But we hit one more small error. Some remaining require statements were not fully replaced. We can fix them by switching everything to import. Then let's rebuild and relink the project again. Now the system is stable. We can run the agent then let's test the command /init. This creates an AI coding agent.md file at the root of the project and initializes the .ai coding agent folder as well. This folder stores sessions, memory, conversation history. We can now see all messages and responses stored correctly. Now let's give the agent a real task, like create a landing page using HTML, CSS, and JavaScript. The agent starts reasoning. It enters the loop and searches for tools. It finds the right tool which allows file creation. Before writing anything, it asks for confirmation. We can approve once, bypass future confirmation, or cancel. I select yes, and it creates index.html, then it creates style.css, and script.js. The agent completes the project successfully. We can open index.html in the browser to see the results. Everything works as expected. Next, we text /restore session command. First, let's kill and reopen the session. Then run /restore session. The system reloads the last conversation automatically. We can then continue with our last task. The agent reads the previous session and understands exactly where we left off. It even suggests improvements for the landing page. We then say add our pricing codes section. The agent updates the project in real time, modifies HTML, updates CSS, updates JavaScript. Everything is applied automatically. This is a real example of an agentic coding assistant built from scratch. Of course, this is only a small part, maybe 10% of what a full system can do. There are still many advanced features missing, like planning mode, skill system, multi-agent orchestration, long-term semantic memory. All of that exists in the full production version available in the official GitHub repository. This kind of system is extremely valuable for AI engineering portfolios. It demonstrates agent design, tool orchestration, memory systems, CLI engineering, and real-world AI workflows. And that's the end of the build. See you next time.